1880, Providence, Rhode Island. The mechanical thunder echoing through Brown and Sharpe's 66,000 square foot factory floor would have sounded like industrial chaos to visiting European engineers. American workers operating cam-driven machines that produced precision bolts without master craftsmen, without guild training, without the generational knowledge European workshops insisted was absolutely necessary for quality manufacturing. Through the rhythmic clank of automated steel, identical parts ejected every 20 seconds with timing that seemed impossible to European observers. No individual setup, no constant manual adjustment, no 3-hour preparation between different components. In Birmingham, England, master craftsmen produced 60 precision bolts per day using techniques perfected over centuries. Each part required individual attention, skilled hands, trained eyes. The Americans were achieving something European engineering wisdom declared could never work: mechanical cams controlling every movement, automated sequences replacing human judgment, production rates that multiplied European output by 3. 8 decades before computer controls, the most efficient manufacturing revolution in industrial history was revealing itself, not through digital programming, but through mechanical genius that modern CNC machines still cannot match for setup speed. The crisis began in 1878, not with mechanical failure, but with mechanical success. American railroads had conquered the continent, stretching 23,000 miles of track from Atlantic to Pacific, but every mile demanded millions of identical components: coupling bolts, rail fasteners, brake fittings, valve stems. The explosion of industrial machinery created equally voracious appetites: steam engines, textile looms, agricultural equipment, mining apparatus, all required precision parts manufactured to exacting standards in quantities that defied traditional methods. In Birmingham, England, the world's acknowledged center of precision manufacturing, master craftsman William Hartley could produce 60 bolts per day using techniques perfected over 3 generations. His manual lathe required constant adjustment for each component, advancing the tool rest, checking dimensions with hand-forged calipers, compensating for variations in steel hardness through subtle pressure changes only experienced fingers could detect. When orders demanded different specifications, Hartley needed 3 to 4 hours reconfiguring his setup, repositioning guides, resharpening tools, calibrating feed mechanisms. Each bolt cost substantially more than American manufacturers could afford, yet European quality remained unquestioned. Hermann Schmidt, representing this established wisdom at the Providence Manufacturers Association, commanded attention whenever he spoke. Trained in the German guild system since age 12, Schmidt had spent 30 years perfecting the ancient relationship between craftsman and material. "Precision cannot be mechanized," he declared to the assembled American engineers, his accent lending authority to words that carried centuries of European experience. Only the human hand and trained eye can ensure quality. American workers lack the generational knowledge of European guilds. You cannot teach a machine to think. Schmidt's arguments resonated because European-trained engineers dominated American manufacturing, importing both techniques and prejudices from the Old World. They controlled the major machine shops in Providence, Hartford, and Worcester, setting standards that favored individual craftsmanship over mass production. American industry found itself trapped, desperately needing millions of parts but constrained by methods that produced hundreds. Joseph R. Brown had recognized this limitation 17 years earlier. Working 14-hour days in his Providence shop, Brown possessed an inventor's restless mind that saw manufacturing problems as mechanical puzzles requiring elegant solutions. His 1861 insight seemed almost heretical. What if machines could be taught to repeat identical movements automatically without human intervention? Brown's 1865 patent for an automatic screw machine described a revolutionary concept: cam-operated mechanisms that controlled every aspect of production through precise mechanical timing. But Brown's vision gathered dust. Potential investors questioned whether mechanical cams could match human judgment. Workers feared automation would eliminate their livelihoods. Even Brown's business partner, Henry Sharpe, remained skeptical about abandoning proven European methods for untested American innovations. The automatic screw machine remained a curiosity, a clever mechanism that solved theoretical problems without addressing practical manufacturing needs. Brown's death in 1876 transferred this challenge to Oscar J. Beale, his most devoted protege. At 34, Beale combined Brown's mechanical genius with an obsessive perfectionist's determination to prove American ingenuity could revolutionize manufacturing. Orphaned at 14 and apprenticed to a clockmaker, Beale understood precision timing in ways that separated him from conventional machinists. He could visualize how rotating cams might control multiple operations with split-second coordination, translating complex manufacturing sequences into elegant mechanical movements. Beale's first attempts in 1878 produced disasters that validated every European criticism. Cams slipped out of sequence, destroying timing relationships that required mathematical precision. Tools broke under automated force that lacked human sensitivity to material variations. Parts varied wildly in dimensions, some undersized and worthless, others oversized and dangerous. The 66,000 square foot Brown & Sharpe factory echoed, with skeptics who called the project Beale's folly and predicted it would bankrupt the company. Each failure reinforced Hermann Schmidt's arguments. During one particularly catastrophic test run, 3 automatic machines destroyed themselves within an hour, scattering broken cams and twisted tools across the factory floor. Schmidt, observing from the gallery, shook his head with the satisfaction of proven wisdom. "Mechanical automation will produce mechanical junk," he told visiting engineers. "No cam can match the touch of a trained craftsman adjusting for material variations." But the pressure continued mounting relentlessly. Railroad orders for 100,000 identical coupling bolts arrived monthly at Brown & Sharpe, quantities that would require 1,500 European craftsmen working full-time to complete. European competitors quoted impossible delivery times, 18 months for orders American railroads needed within 60 days. Machine builders in Detroit demanded precision gears in quantities that exceeded the entire output of Birmingham workshops. American industry faced an existential choice. Traditional European methods, despite their undeniable quality, could never scale to meet American demands. The continent's industrial expansion had created manufacturing requirements that guild systems, designed for limited production runs, simply could not satisfy. European suppliers controlled quality standards but lacked production capacity. American manufacturers possessed neither quality nor capacity using conventional approaches. Beale understood that solving this puzzle meant more than improving Brown & Sharpe's profits. American industrial independence depended on mechanizing precision manufacturing, teaching machines to achieve consistency that matched European craftsmen, while producing quantities that surpassed European imagination. The automatic screw machine represented democracy applied to manufacturing, making quality production accessible to ordinary workers rather than guild-trained masters. Standing in his Providence factory amid the wreckage of failed experiments, surrounded by skeptics convinced that American ambition exceeded American capability, Beale faced the challenge that would define industrial history. Could mechanical cams replace centuries of accumulated human skill? Could American ingenuity overcome European craftsmanship through intelligent automation? The answer would determine whether American manufacturing achieved independence or surrendered leadership to the old world forever. Beale's breakthrough arrived through an unexpected source in 1880, the mechanical sophistication of a player piano. Walking past Steinway Hall on Westminster Street during a February evening, he paused to watch the automated instrument perform a complex Chopin nocturne with perfect timing and expression. The player piano's rotating perforated cylinders controlled dozens of keys simultaneously, each whole, triggering precise mechanical actions at exactly the right moment. If rotating drums could orchestrate musical notes with such intricate timing, Beale realized, why couldn't similar mechanisms orchestrate machine tool operations? The revelation transformed his approach completely. Instead of trying to replicate human decision-making through mechanical means, Beale would create a mechanical brain that executed predetermined sequences with clockwork precision. He spent sleepless weeks sketching cam profiles, calculating rotation speeds, and designing drum mechanisms that could control every aspect of bolt production through pure mechanical timing. His master cam system employed 6 rotating drums, each precisely machined to control specific operations during the manufacturing cycle. The first drum governed stock advancement, feeding steel rod into the machine at exactly the right moment. The second controlled spindle rotation speed, ensuring optimal cutting conditions throughout the operation. The third managed tool feed rates, advancing cutting implements at calculated speeds to maintain dimensional accuracy. The fourth coordinated clamping mechanisms that held workpieces securely without distortion. The fifth operated threading tools with mathematical precision. The sixth controlled part ejection, removing completed components while positioning the machine for the next cycle. Each cam required extraordinary precision in its manufacture. Beal worked with Brown Sharpe's most skilled pattern makers to create templates accurate to within 0.02 of an inch. The drums themselves were cast from specially selected iron, then machined on the factory's finest engine lathes to ensure perfect concentricity. Every rise and fall on the cam surface was calculated to produce specific tool movements at predetermined intervals during the 20-second manufacturing cycle. The sequence Beal programmed into his mechanical brain followed logical industrial choreography. First, the stock advancement cam fed steel rod forward exactly 1 bolt length. Simultaneously, the clamping cam engaged holding mechanisms that secured the material without crushing it. The spindle cam initiated rotation while the tool feed cam advanced the cutting bit into the spinning steel. Threading operations began precisely when the turning cuts were completed, controlled by the fourth cam's timing. Finally, the parting tool separated the finished bolt while the ejection cam removed it from the machine, clearing space for the next cycle to begin immediately. William Thornley arrived in Providence during March to evaluate American manufacturing capabilities for the British Board of Trade. A graduate of Manchester Technical Institute and veteran of 30 years in Birmingham's precision manufacturing district, Thornley carried himself with the confidence of someone representing the world's leading industrial nation. British engineering dominated global markets through superior quality control, and Thornley intended to document American shortcomings for his official report. Beal demonstrated the automatic screw machine for Thornley on a cold Tuesday morning, feeding steel rod into the mechanism while explaining the cam timing system. Thornley observed with professional skepticism, taking notes in a leather-bound journal and periodically checking his pocket watch to verify Beal's production claims. When the 20th bolt emerged identical to the first, Thornley examined both components with precision calipers, measuring diameter, thread pitch, and overall length. Mechanical automation will produce mechanical junk, Thornley declared after completing his inspection. No cam can match the touch of a trained craftsman adjusting for material variations. These parts may appear acceptable, but sustained production will reveal systematic flaws that human oversight prevents. He gestured toward the cam mechanisms with obvious disdain. Birmingham craftsmen adjust their techniques continuously, compensating for steel hardness variations, temperature changes, tool wear patterns. Your mechanical brain cannot think. Beal listened respectfully, but recognized the fundamental misunderstanding in Thornley's criticism. European craftsmen achieved quality through individual adjustment, correcting for variables during production. American automatic machinery achieved quality through elimination of variables before production began. The cams were machined to mathematical precision, removing human inconsistency from the manufacturing process. Steel rod was selected for uniform properties, eliminating material variations. Cutting speeds were calculated for optimal performance, removing guesswork from tool operation. Thornley's visit extended through 2 weeks while he documented American manufacturing methods for his comprehensive report. He observed traditional machine shops in Providence, Hartford, and Springfield, interviewing European-trained master craftsmen who confirmed his expectations about American industrial limitations. These workshops produced quality work using familiar European techniques, but their output remained constrained by conventional manning requirements and setup procedures. The automatic screw machine represented something entirely different, a manufacturing philosophy that Europeans had never seriously considered. Where European methods relied on accumulated human experience to manage variables, American automation eliminated variables through systematic mechanical control. Where European quality depended on individual craftsman skill, American consistency emerged from machine precision that surpassed human capabilities. During his final demonstration visit, Beale operated the automatic screw machine continuously for 4 hours, while Thornley observed and measured random samples, 144 bolts per hour, each matching specifications within tolerances that exceeded Birmingham workshop standards. Setup time for different specifications required only 15 minutes to swap pre-machined cam sets, compared to 4 hours for European manual reconfiguration. Thornley's official report to the British Board of Trade acknowledged American production rates but questioned long-term reliability. Colonial enthusiasm for mechanical shortcuts may produce temporary advantages, he wrote, but sustained manufacturing excellence requires human judgment that no mechanism can replicate. British quality standards will ultimately prevail over American quantity methods. Yet privately, Thornley recognized that Beale had achieved something unprecedented in precision manufacturing. The automatic screw machine combined European-level quality with American-scale production, creating manufacturing capabilities that challenged fundamental assumptions about industrial organization. Whether mechanical brains could truly replace human experience remained uncertain, but the implications were becoming impossible to ignore. The first fully successful production run commenced on April 15, 1881, with Henry Sharpe observing from the factory floor as Beale initiated the automatic sequence. The Mastercam system engaged with mechanical precision, advancing steel rod while spindle rotation reached optimal cutting speed. Tool engagement occurred exactly as programmed, removing material in precise increments, while threading operations followed in perfect timing. 20 seconds later, the first bolt dropped into the collection bin, followed by another 20 seconds later, then another. For one complete hour, the automatic screw machine maintained this rhythm without deviation. 180 bolts emerged from the mechanism, each machine to identical specifications through purely mechanical control. Sharpe examined random samples with precision measuring instruments, discovering dimensional consistency that exceeded his expectations. More significantly, the 100th bolt matched the first bolt to within 0.02 of an inch, a level of repeatability that European hand production could never achieve consistently. The implications became immediately apparent. European craftsmen producing 60 bolts daily represented the absolute peak of human capability using traditional methods. The automatic screw machine had tripled this output while maintaining superior dimensional accuracy. Setup time for different specifications required only 15 minutes to swap pre-machined cam sets, compared to 4 hours for European manual reconfiguration. The mechanical brain had solved the fundamental manufacturing equation: precision plus speed plus consistency. Word of Beale's success spread rapidly through American industrial circles. Orders arrived from railroad companies desperate for coupling hardware, machinery manufacturers needing precision fasteners, and firearms producers requiring identical components in unprecedented quantities. The Pennsylvania Railroad alone contracted for 500,000 bolts monthly, quantities that would require 800 European craftsmen working full-time to complete using traditional methods. Sharpe recognized the scaling opportunity immediately. Brown and Sharpe possessed the technical capability to manufacture automatic screw machines in quantity, replicating Beale's mechanical innovations across multiple production units. By October 1881, the company had completed 50 automatic machines, each equipped with interchangeable cam sets for different component specifications. Factory floor space expanded to accommodate the growing operation, with dedicated areas for cam storage, steel rod preparation, and finished parts inspection. The scaling challenge demanded systematic organization that transcended individual machine operation. Beale developed standardized procedures for cam changing, ensuring that any trained operator could swap configurations within the 15-minute target. Steel rod procurement required coordination with suppliers who could deliver material meeting uniform specifications, consistent hardness, precise diameter, reliable chemical composition. Quality control procedures monitored random samples from each machine, maintaining statistical records that documented dimensional consistency across the entire production system. By 1883, Brown and Sharpe operated 200 automatic screw machines across 3 shifts, producing 400,000 parts weekly. The Providence factory employed specialized workers in roles that European workshops had never imagined. CAM preparation specialists who machined timing drums to mathematical precision, setup operators who could reconfigure multiple machines simultaneously, and quality inspectors who monitored statistical variation patterns across dozens of production units. European competitors found themselves facing an impossible situation. Brown & Sharpe's weekly output exceeded what Birmingham's entire precision manufacturing district could produce in 6 months using traditional hand methods. American prices dropped to levels that made European imports economically unfeasible, while delivery schedules shortened from months to weeks. British and German manufacturers watched established customers shift orders to American suppliers who offered superior consistency at lower costs with faster turnaround. The transformation extended far beyond Brown & Sharpe's Providence operations. Automatic screw machines began operating in Detroit automotive plants, where Henry Ford's early experiments with moving assembly lines demanded thousands of identical fasteners. Chicago agricultural equipment manufacturers installed automatic systems to produce plow bolts and cultivator pins in quantities that supported mechanized farming across the expanding Midwest. Cleveland steel fabricators used automatic machines for structural bolts that connected the framework of America's emerging skyscrapers. By 1885, Brown & Sharpe had achieved complete dominance in American small parts manufacturing. The company employed 1,400 workers, becoming the world's largest machine tool manufacturer through systematic replication of Beal's mechanical innovations. The Providence facility covered 33 acres, with specialized buildings for CAM production, automatic machine assembly, steel rod processing, and finished parts warehousing. Annual revenue exceeded $2 million, establishing Brown & Sharpe among America's most profitable industrial enterprises. The automatic screw machine success attracted international attention that European engineers could no longer dismiss. Delegations from British, German, and French manufacturing associations visited Providence to observe American production methods firsthand. They witnessed mechanical precision that exceeded European hand craftsmanship, while achieving output rates that defied traditional manufacturing assumptions. The CAM-operated systems represented a fundamental challenge to European industrial supremacy that had dominated global markets for centuries. Beal's mechanical brain had proven its superiority through sustained commercial success rather than theoretical arguments. American industry had solved the precision manufacturing puzzle through intelligent mechanization that democratized quality production. Where European methods required decades of apprenticeship to develop craftsman skills, American automatic machines could be operated by workers with minimal training. The mechanical systems eliminated human variability from manufacturing processes, achieving consistency that individual craftsmen could never match regardless of their experience level. The broader implications extended throughout American industrial development. Precision parts produced by automatic screw machines enabled complex machinery that would have been impossible using European supply methods. Steam engines, textile looms, agricultural equipment, mining apparatus, and transportation systems all benefited from reliable fastener supplies that met exacting specifications at reasonable costs. American manufacturing had achieved independence from European suppliers while establishing technological leadership that would define industrial progress for generations. Standing in his Providence factory amid the rhythmic operation of 200 automatic machines, Beal had witnessed the vindication of American engineering philosophy over European craftsmanship traditions. The mechanical revolution had succeeded beyond his most optimistic projections, transforming Brown & Sharpe from a struggling Providence workshop into the world's dominant precision parts manufacturer. Yet this triumph would soon face its greatest test, as rushed government contracts and ambitious production schedules created conditions for catastrophic failure that threatened everything Beal had achieved. The government contract arrived in March 1886 with specifications that seemed routine: 500,000 rifle bolts for the expanding United States Army, delivery required within 90 days to support infantry modernization programs across Western territories. The Ordnance Department demanded exacting tolerances for bolt threading and head dimensions, but these requirements fell well within capabilities that Brown & Sharpe's automatic screw machines had demonstrated consistently for 5 years. Sharpe viewed the contract as validation of American manufacturing superiority, while Beale welcomed the opportunity to prove mechanical automation could meet military precision standards. The challenge lay not in technical specifications, but in production scheduling. 500,000 bolts represented nearly 2 months of total factory output, requiring dedicated allocation of 30 automatic machines operating across all 3 shifts. To meet the delivery deadline, Beale coordinated with multiple steel suppliers, accepting rod stock from mills in Pittsburgh, Cleveland, and Chicago, rather than relying solely on the carefully selected Providence suppliers who had provided material for previous contracts. The disaster began during the second week of production, when inspector reports noted unusual cam wear patterns on machines processing steel from the Chicago supplier. The rod stock appeared identical to specification, correct diameter, proper surface finish, acceptable straightness measurements, yet the material exhibited unpredictable hardness variations that caused cutting tools to bind unexpectedly. Beale adjusted cam timing to compensate for the harder material, increasing cutting speeds while reducing feed rates to maintain dimensional accuracy. These modifications temporarily resolved the immediate problems, but they placed additional stress on the cam mechanisms that were never designed for continuous operation under variable loading conditions. The precisely machined cam surfaces began showing microscopic fractures, where increased cutting forces exceeded design limitations. Steel suppliers had substituted lower-grade material to meet volume requirements, introducing chemical inconsistencies that European-trained metallurgists would have detected immediately through traditional testing methods. The catastrophic failure occurred during the third shift on April 23rd, when 30 machines processing rifle bolts simultaneously experienced cam seizure as accumulated stress fractures reached critical failure points. The precisely timed mechanical systems that had operated flawlessly for 6 years suddenly became uncontrolled industrial hazards. Cams shattered under excessive loading, releasing broken steel fragments that scattered across the factory floor like shrapnel from artillery explosions. Workers fled the production area as automatic machines destroyed themselves in mechanical chain reactions that Beale's safety systems had never anticipated. Spindles continued rotating while broken cams lost timing control, causing cutting tools to advance into solid steel at maximum feed rates. The resulting impacts shattered tool holders, bent machine frames, and sent broken components flying through the factory space with lethal velocity. Steam pipes ruptured from flying debris, filling the workspace with scalding vapor that forced complete evacuation of the third shift. The entire night crew of 80 workers abandoned their positions, leaving 30 automatic screw machines to complete their self-destruction without human intervention. By morning, Brown & Sharpe's most productive manufacturing area resembled a battlefield, littered with twisted metal, broken cams, and thousands of partially completed rifle bolts scattered among the debris. The mechanical brains that had revolutionized American manufacturing lay silent, their precision timing mechanisms reduced to expensive scrap metal. European critics seized upon the disaster as vindication of traditional craftsmanship principles. Hermann Schmidt issued statements to technical journals emphasizing that American speed sacrifices safety and quality, while William Thornley's follow-up report to the British Board of Trade concluded that mechanical automation creates systemic vulnerabilities that human oversight prevents. British and German manufacturers used the Providence disaster to argue that automated production methods were inherently dangerous, unreliable, and unsuitable for precision manufacturing applications. The immediate consequences extended far beyond damaged machinery and injured reputation. Military contracts were canceled as the Ordnance Department investigated safety procedures at automated manufacturing facilities. Commercial customers demanded inspections of their existing orders, discovering dimensional variations that had been acceptable during normal operations but became suspect following the catastrophic failure. Railroad companies postponed new orders while reviewing quality control procedures with their legal departments. For 8 months, Brown & Sharpe struggled to maintain operations as orders disappeared, and competitors regained market share through aggressive pricing strategies. European suppliers promoted their traditional hand manufacturing methods as inherently safer than American mechanical automation, winning back contracts that had been lost to automatic production 5 years earlier. Newspapers across New England mocked Yankee mechanical madness, while financial publications questioned whether automation represented industrial progress or dangerous overreach. Brown & Sharpe stock plummeted from $38 per share to $12 as investors lost confidence in automated manufacturing methods. The company's financial position deteriorated rapidly as fixed costs continued, while revenue collapsed. Sharpe faced pressure from board members who questioned the wisdom of abandoning proven European techniques for experimental American innovations that had produced spectacular failure alongside previous success. Workers demanded return to manual production methods that offered job security through individual skill rather than dependence on mechanical systems that could fail catastrophically without warning. The Providence Machinists Union organized meetings where members shared concerns about automation's impact on worker safety and employment stability. Many skilled operators requested transfers to conventional machine shops where traditional techniques provided predictable working conditions. The 33-acre Providence complex sat mostly silent through the summer and fall of 1886, a monument to overambition and misplaced confidence in mechanical solutions. Automatic screw machines that had produced millions of precision parts now stood idle, their cam mechanisms removed for inspection and repair. The mechanical revolution that had transformed American manufacturing faced potential extinction as critics declared that human judgment could never be replaced by mechanical timing, regardless of previous successes. Beale confronted the possibility of complete failure as company dissolution became a realistic scenario. The automatic screw machine had proven vulnerable to variables that traditional manufacturing methods handled through individual craftsman adjustment. Whether mechanical automation could survive this fundamental challenge remained uncertain, as American industrial leadership faced its greatest test, since the concept of automated precision manufacturing had first challenged European dominance. Beale's redesign consumed 8 months of intensive engineering work, beginning with fundamental analysis of every component failure from the April disaster. Working with metallurgists from Sheffield Steel Company and mechanical engineers from Stevens Institute, he identified 3 critical vulnerabilities in the original automatic screw machine design. Cam materials had been insufficient for sustained high-stress operation. Safety systems had failed to prevent cascading mechanical failures, and setup procedures had relied too heavily on individual operator judgment, rather than systematic standardization. The refined cam design employed heat-treated alloy steel rather than conventional cast iron, increasing mechanical strength by 40% while maintaining precision machining tolerances. Each cam underwent systematic stress testing using hydraulic loading equipment that simulated 10 years of normal operation within 48 hours. Surface hardening treatments extended cam life expectancy from 2 years to 7 years under continuous production conditions. The new materials cost 3 times more than original components, but they eliminated the catastrophic failure modes that had destroyed 30 machines simultaneously. Safety interlocks represented completely new technology in automated manufacturing systems. Beale developed mechanical sensors that monitored cam position continuously, automatically stopping machine operation when timing mechanisms deviated from programmed sequences. Tool breakage sensors detected cutting implement failures within milliseconds, preventing damaged tools from destroying workpieces or cam mechanisms. Emergency shutdown systems could halt entire production lines instantly when any single machine detected dangerous operating conditions. The standardized setup procedures eliminated human variability from cam changing operations through systematic documentation and specialized tooling. Beale created detailed instruction sheets that specified exact sequences for cam removal, inspection, installation, and timing verification. Custom wrenches and positioning fixtures ensured that any trained operator could complete cam changes within 8 minutes, regardless of their individual experience level. Quality control checklists required verification of 12 specific measurements before resuming production after any configuration change. The public demonstration on September 15, 1887, attracted representatives from major American manufacturers alongside skeptical European observers who expected continued evidence of automated manufacturing limitations. Beale had arranged for master craftsmen from Birmingham and Sheffield to operate traditional manual lathes alongside the redesigned automatic screw machines, providing direct comparison of European methods against American mechanical innovations. The demonstration began with both systems producing identical bolt specifications using the same steel rod stock. European craftsmen worked with practiced efficiency, adjusting their manual lathes for optimal cutting conditions while monitoring dimensional accuracy through frequent measurements with precision calipers. Their techniques represented centuries of accumulated knowledge translated into individual hand movements that achieved remarkable consistency through human skill alone. The automatic screw machines operated with mechanical precision that surpassed human capabilities, maintaining exact timing relationships between all operations throughout the production cycle. Cam-controlled tool movements eliminated the dimensional variations that inevitably occurred with manual operation, while programmed sequences ensured identical treatment of every workpiece. The mechanical brains executed their manufacturing choreography without fatigue, distraction, or gradual skill degradation that affected even master craftsmen during extended production runs. After 4 continuous hours, the results validated Beal's mechanical philosophy completely. European craftsmen had produced 125 bolts of exceptional individual quality, each requiring manual adjustment and careful monitoring. Throughout the manufacturing process, the automatic machines had produced 1,000 bolts with dimensional consistency that exceeded European standards, requiring no human intervention beyond initial setup and periodic material feeding. The setup demonstration provided equally dramatic evidence of American superiority. When specifications changed to require different bolt dimensions, European craftsmen needed 4 hours to reconfigure their manual lathes, repositioning tool rests, adjusting feed mechanisms, resharpening cutting implements, and calibrating measurement systems. The automatic machines required 8 minutes to swap pre-machined cam sets, immediately resuming production with identical precision for the new specifications. European observers could no longer question the fundamental advantages of mechanical automation over traditional craftsmanship methods. William Thornley acknowledged that American innovations had achieved manufacturing capabilities that European workshops could not match using conventional techniques. British and German manufacturers began placing orders for Brown and Sharpe automatic screw machines, admitting that mechanical precision offered competitive advantages that justified abandoning centuries-old production methods. By 1890, American industrial transformation had reached complete fulfillment. 200 factories across the United States operated Brown and Sharpe automatic screw machines, producing 50 million precision parts annually through mechanical systems that required minimal human oversight. Detroit automotive plants, Connecticut firearms manufacturers, Massachusetts textile machinery builders, and Pennsylvania railroad equipment suppliers all relied on automated production methods that had originated in Beal's Providence workshop. The broader implications extended throughout global manufacturing as European competitors recognized American technological leadership. British firms purchased automatic machines to remain competitive in precision parts markets, while German manufacturers sent engineering delegations to study American production methods. The mechanical revolution that had begun with player piano inspiration had fundamentally altered international industrial relationships, establishing American manufacturing supremacy through intelligent mechanization rather than traditional craftsmanship approaches. By 1900, the principles of cam-operated automation had spread throughout American manufacturing in applications that exceeded Beal's original vision. Textile machinery employed automatic mechanisms for thread handling and pattern control. Agricultural equipment manufacturers used cam-driven systems for seed metering and harvesting operations. Mining apparatus incorporated automated safety systems that protected workers through mechanical monitoring rather than human supervision. The ironic legacy became apparent decades later when computer-controlled manufacturing systems replaced mechanical automation, yet required significantly longer setup times than Beal's 19th century innovations. Modern CNC machines needed 45 minutes to 2 hours for programming verification, tool path calculations, and fixture adjustments between different production runs. Brown & Sharpe's 1880 cam machines had achieved job changes within minutes through simple mechanical cam exchanges, demonstrating efficiency that digital technology had failed to match despite superior computational capabilities. Beal's final assessment, written in 1900, captured the essence of American manufacturing philosophy that had revolutionized global industry. American manufacturing learned to think differently about precision. We didn't make better craftsmen, we made craftsmanship unnecessary. The machine became the master, and the master became the teacher. The automatic screw machine had democratized precision manufacturing, proving that mechanical intelligence could exceed human capabilities while making quality production accessible to ordinary workers rather than guild-trained masters.